So this program is meant for graduate students to be able to propose their own independent scientific, irrespective of their supervisor, and it $5,000 for 1 year term to. The only stipulation is that the teams that apply for this funding have to be interdisciplinary. So these two different grad students from two different coming together to work together. So the idea is that when grad students are, at Phoenix, chatting with their friends and talking about their research ideas, they say, "Oh, you're doing this and I'm doing this. Wouldn't it be cool if we did something together?" This is the opportunity for students to get funding to do that kind of idea. You get funding to class materials, equipment, do whatever it is you project, just like what faculty do program. And so the next call for proposals will go out in January with funds. So you or your students are interested in this opportunity, please watch for the announcement. And so with that, I will introduce our first group of winners from this past year. And today, what they're doing is giving a progress report because they received the funding in around May and had the summer to get started on the project. And so this is sort of the update, the interim update, and there will be a final presentation. So the first team that wants to introduce is Andy Marway, Anthony D'Angelo, and Michael Solejos.
Pretty good, Solevsky.
And they are from the groups of Boyang Zhang and Ryan Wiley, and they've been working on modeling drug clearance using. So I'll turn it over to you for the presentation.
Thank you. So welcome everyone. Thank you for coming to our presentation for our BIMR progress report. For those of you who don't know me, my name is Mandeep Marway, and I, along with my colleagues, Anthony D'Angelo and Michael Solejos, will be discussing how we will go about modeling drug clearance using the iFlow plate T. Oh, damn it.
Click first.
Okay, thanks.
So the core component of this project is, of course, developing the clearance model itself. Imagine a mug filled with coffee. If that coffee is not being, if you're not taking a sip of that coffee, then it just sits there. Now compare this to the idea of locally bringing drug into the brain. If we had a way of doing this, if it was like the coffee mug, that drug's not going anywhere. But drugs don't just sit in the treatment site. In reality, drugs clear from the treatment sites over time. So if I accidentally broke my mug and now there's a hole in it, but I'm stubborn and I want to use my BIMR mug, then, well, it's going to clear out of the mug over time. Same with how drug will clear out of the treatment site over time. We'll see drug concentrations decrease. And so when we're talking about drug clearance here, we're talking about drug clearance from one location to another. This is the idea of the compartment model that you might have heard of in drug classes. So in this case, we're talking about the brain tumor site, the drug going into some other compartment, which in this case is just outside of the brain. So the drug is no longer accessible to perform anti-cancer action. Modeling drug clearance is important. If you imagine the case of the mug where the coffee is not going anywhere, or the case where drug's not going anywhere in the brain, drug concentration is constant. This is what we see in standard in vitro, standard well plate models. Whereas in the biological context in the brain, that's not actually what's happening. We're seeing drug concentration decrease over time. So to reiterate, this idea of using a coffee mug as our example here is supposed to represent this idea of in vitro models where you have a single well with no continuous drug clearance. In cancer studies, you often see a layer of cells along the bottom of the well. This is known as a cancer monolayer. In cell culture media with drug just suspended within it. Now, these are actually pretty good for understanding drug binding and anti-cancer action, but the question is if there's going to be differences in activity in the actual tumor environment. Because we don't have continuous drug clearance, we also can't tell like what's going to happen in terms of activity when we're losing drug concentration over time. And we also have a poor sense of what happens to the drug and where it ends up. So in the case of our coffee mug example, it's the difference between if we're able to control it and quickly catch that coffee with a bowl versus it spilling and all over you and potentially harming you. In the case of a patient, it's the difference between the body being able to control concentrations and clear it out after it does its anti-cancer action versus it potentially causing harm somewhere where it gets stuck in the body.
Okay, so now that we know why we need clearance, allow me to introduce you to the iFlow Plate T. For those of you who are familiar with some of the work that's done in the Zhang lab, you would have heard of the iFlow Plate. The iFlow Plate is a device that's created on a 384 well plate. It contains 128 different networks that would allow for you to look at drug administration as well as tissue response to those drugs. However, something that it doesn't inherently have is a clearance aspect. With the iFlow Plate T, we're using the same idea of being able to administer the drug, but we also have that additional clearance well that's denoted as CL that would allow for continual clearance, which would give us an idea of how not only our cells would metabolize our drug, but also what sort of toxins would be released, any byproducts of our drug, as well as the drug itself. So before we could actually start using our platform, we wanted to confirm that in the presence of a pressure gradient, where we would have high pressure in the 3 adjacent wells and low pressure in our clearance well, if we were able to push our drug out only into the clearance well. For visualization purposes, we used FITSI labeled dextran as a potential model. And what we found over 24 hours was that majority of our dextran was being cleared into our clearance well and negligible amounts were going into the outer wells. After 24 hours, we also collected the samples to try and determine what our average flow rate was. So we collected it, weighed out our sample, and using density, we determined what our volumetric flow rate was, and it was approximately 2.7 microliters per hour on average. So then the next step was to decide how we wanted to administer our drug. Again, using dextran as a model, we decided that for our purposes, since we were looking at more toxic drugs, we wanted to model local injection. So in order to model that, we incorporated dextran within a 3% agarose, and we casted it above a fibrin gel, which would act as our extracellular matrix for when we introduced our cancer cells. And we looked at the diffusion of the dextran over a course of 48 hours. And what we found was that the 4 kilodalton dextran diffused more rapidly than the 65 kilodalton dextran, and it only cleared out into the clearance well, showing that both our pressure gradient was working and that our molecular diffusion made sense.
So now we validated our model just using dextran. So now we validated our model using dextran just as a sample macromolecule. But for future work, what we want to do is we want to move on to drugs that have like potential therapeutic relevance. So the one we're proposing on using is interferon gamma. The reason we're interested in it is because in certain treatments, such as anti-cancer treatments, this protein, it could potentially have therapeutic benefits. However, it can be very highly toxic if it doesn't stay at the cancer site. So one thing we want to do is we want to see if we can measure clearance of interferon gamma using our model. So what we can do is with the high pressure well kind of in the middle, we can sort of make this mimic like a tissue compartment. So we can add our interferon gamma just in some sort of a drug depot. We're just going to use agarose for proof of concept. And then we're going to see if it's going to enter in through the fibrin gel, just sort of mimicking the tissue, and then see if it gets cleared out into the clearance well. So we're predicting based on the results of the dextran, we'll see the interferon gamma being cleared to the low pressure well at the back without necessarily going into the outer high pressure wells at the side. But then we know that when we're administering a drug, it doesn't just necessarily get cleared out. It is going to be uptaken by cells in the area, and we're hoping it is going to have some therapeutic benefit. So what we plan to do is we plan to see how this drug clearance is going to change when we do have cells present. So we can even incorporate a 3D cell model into this bottom fibrin gel. And what we're going to expect is not all of the drug should be cleared, but some of it will be uptaken by the cells. We are going to get some drug metabolism. So we can compare these results back to the results where we didn't have any cells present.
And with that, we'd like to thank the entire BIMR team, especially Dr. Adjanoff and Florian, for making today possible, and our lovely supervisors, Dr. Boyang Zhong and Dr. Ryan Wiley, and Sahib Marway, who worked with me over the summer to help us with manufacturing and assembling the devices. Thank you. Would be the fluid pressure. No, just gravity. Yeah, just by having higher volumes, we're just pushing everything. Kevin?
And then, in terms of the connection,
Yes, so those channels we milled using a milling machine, and yes, they act as microfluidic channels between the wells for stuff to flow through.
Thanks for saying this much. My question is, I mean, you apply pressure to actually make sure that the drug goes out.
Yes.
I mean, but in the biological system, it's a different mechanism. It's not a pressure. I mean, so the concentration gradient. How do you relate this pressure gradient to the field biological system? Like the different physical.
I would say, like, in the case of using this model, it would depend on the specific research question you're asking. Like, if I were to use the device, personally, I'd be thinking in terms of if the drug is just physically decreasing in concentration over time, how is that going to affect the ability of my drug or whatever I put into the system to be able to function properly? So for sure, like if you're looking at specifically concentration gradients, you would have to modify the system for sure to actually assess that, if that's like what your research question entails.
And when we use the standard iFlow plate, we don't really have a pressure gradient there. That one is purely based on concentration gradients when we see passage. $64.
So we all 64 spots on plate or like monitor 60.
Theoretically, you can. For the most part, when I'm running these experiments, I do run all of them. And we do have some empty wells that aren't milled into anything that we can use as potential reservoirs where we add PBI in order to prevent evaporation. So yes, theoretically, you can use all 64 of them, and I do. What's it?
So for the pressure.
So currently we haven't really applied it, but when we start running our cell experiments with the media changes, we will increase the volume, and from the clearance well, we'll be aspirating out and re-administering the baseline amount. So the pressure is not significantly dropped within the couple of days in between media changes. So the frequent media changes would allow for us to maintain the pressure.
If I saw this correctly, like
just in the center well. Yes.
Can you tell me more about the pipe? Gel, is it a polymer?
It's a hydrogel. And we use it as an extracellular matrix.
So is there tunability of the clearance in the sense that, like, do I want a model that shows me 10%, 20%, 30%, 50%, 75% clearance? Like, is there a way to turn that dial in your design? Because look, around the room, we're incredibly diverse. We're probably going to, distribute drugs differently. So I'm just trying to think at a personalized level, or even sort of like clearance response level. Like, do you have the ability to tune the plate to capture that?
Yes, we do.
How would you do that?
So, for example, if you want to decrease the flow rate into the clearance well, if you increase the volume, your starting volume for the clearance well, it'll decrease the pressure gradient, which would then allow for less clearance. And if you want to increase the clearance rate, do the opposite. So decrease your starting volume.
Can I kind of come in on that too, and related to the fiber comment? Would you keep that fixed, or is there value in like tweaking the fiber to actually, like, would that ever influence the clearance?
It will. So the more porous the extracellular matrix, the slower the clearance rate, or slower the diffusion rate. So for the case of fibrin, it's an enzymatic cross-linking. So if we increase the thrombin concentration, it'll make our cross-linking more dense, causing our gel to be more porous. Less porous. So that would also decrease our clearance rate.
And could you think of like a health versus disease state where you actually may want to model that? Like, maybe in a healthy situation, you ECM is this, and then in your disease situation, you ECM is that. So, like, is there a value in pursuing that in the plate to have both like healthy and disease status?
Yeah, so I know you do fibrosis stuff. And so I know that in fibrosis tissue, the extracellular matrix is extremely dense. So that would probably be one of the situations in which you would want to modify and look at clearance through a more dense extracellular matrix.
Okay, thank you for that. Let's thank our first meeting. Okay, great. For the second talk, so the second team is composed of Eve Gonzalez Martinez and Ron Singer from the groups Jade Rhoda and They're going to tell us about your work on the development of a mixer for homogeneous mixing of cells.
Thank you. So I'm just going to pull up my laser if I can. Oh, I can't. Can't find my mouse. That's okay. I'll point at this. So yeah, so we're developing a mixer for homogeneous and gentle mixing of cell suspension into silk pump, which is a viscous bioink, and that's for the application of extrusion bioprinting. Is there a trick to this, or? Oh, click. Oh, I see. There's my mouse. Okay. So extrusion-based 3D bioprinting is becoming more and more important in biomedical research. You just mess something up. Shoot. I know every computer is different.
I just wanted to get rid of the, here. Okay. Here you go.
And you should be able to just use the mouse. It works.
Thank you. Oh. Sorry.
Hot corners. All right.
Okay, I'm gonna leave it like that. So extrusion-based 3D bioprinting is becoming more and more popular because it gives people a way to create custom cell-laden 3D biostructures. And this is most useful for tissue engineering and microphysiological system development, among other applications. However, the bioinks, or the materials that are used for extrusion bioprinting, they're often high viscosity, and this makes it difficult to mix with cells. So if you want to try and keep your cells viable, you might end up with low homogeneity. If you want to really mix it well, you might end up with low cell viability in your bioink. So there's a need for a simple and reproducible method for gently mixing cells with viscous materials, viscous bioinks. So just briefly, there are two major objectives for the project. The first being developing and characterizing a bioink based on silk fiber and methacrylate, or SILCMA. And the other major objective is developing a static mixer for incorporating cells within this bioink. And it would also be applicable to other viscous bioinks with similar properties. So just briefly, what we're going to talk about is the composition, rheology, and printability of the SILCMA bioink. And on the mixer side, we're going to talk about mixer geometries, so the ones that we've evaluated so far, some CFD or computational fluid dynamics simulations, and mixing performance. And then we'll describe a tiny bit of our plans for mixing cells and cell viability.
So as Brian mentioned, our first objective was related to developing a new SILCMA bioink. It's important to mention that the SILCMA per se is a liquid that flows, so it's not suitable for extrusion 3D bioprinting. Therefore, you need to include a rheology modifier. And in our group, we have been developing different rheology modifiers, and one of them is Capable, which is the one that we're going to be using today. We are using in this project. So the first part of the project was focused on.
Oh, do you do more of that? Oh, sorry.
Was focused on synthesizing SILCMA. To do that, we started with silkworm cocoons, the original cocoons. Then we processed that materials, and we were able to make silk fibroin by a reaction with glycidine methacrylate that introduced these double bonds here that allow us to photocross-link the bioink during the printing process. So the normal purification that we used was dialysis, and then we obtained the solid SILCMA material after freeze.
We press space.
Okay. So after we synthesize our SILCMA, we use Capable and Lab. Lab is a photo initiator that we use that allows us to photocross-link at 405 nanometers blue light, which is more suitable, more compatible with the cells. So we use Capable, SILCMA, and Lab, and then we mix all that using two syringes, and then we centrifuge, and we have our bioink. These bioinks that we're gonna be showing here are pre-inks that then we're gonna mix with the cells, and we're gonna obtain our final bioink. Okay. So when you're working with extrusion 3D bioprinting, there are two main characteristics that you want to look for in your biomaterial. First, shear thinning. Shear thinning implies that when you increase the shear rate, the viscosity decreases. So that's important because when you have a solution that is really viscous, you need to apply a lot of pressure to be able to extrude it. And if your material doesn't have shear thinning, then your cells are gonna die basically inside the material. So the idea is that you have shear thinning to preserve the cell viability. And as you can see here, we tried 3 different concentrations of SILCMA using a really low concentration of the rheology modifier, Capable. We tried 1, 3, and 5% of SILCMA, and in all cases we have similar viscosity, and in all cases shear thinning here. The second property that we need to look for is isotropy, and it's really important because this is a time-dependent property where basically give you an idea of how good it's gonna be to your ink for the print. We have three main areas here. The first one is a low shear rate, which basically you have a high viscosity, then you suddenly increase the shear rate to 500, and the viscosity decreases. And after that, you go back to 1 hertz at your shear rate, and the viscosity recovers, which implies that you're going to be able to form to extrude a fiber, and then you're going to have the initial viscosity, and you're going to preserve your printability. You're going to have a good printability and shape fidelity. After analyzing all these inks, we went to the cross-linking. So, as mentioned, we used a photo initiator for the cross-linking, and then we made some pots and characterized the mechanical properties of those materials. And here I'm showing G prime, Hydrogen prime, and compression modulus. G prime is the storage modulus, loss modulus, and compression modulus. And again, for 1, 3, and 7%, we're able to tune the mechanical properties of the materials, which implies that if we want to mimic some kind of tissue, for example, we can tune those mechanical properties based on the properties of the tissue. And after that, we went to bioprint. As you can see here, we have two different models. We have a cylinder and we have a mesh, and we were able to print the models with high printability. And I want to show you a video of one of the cylinders that we printed. As you can see in the video, we have a high stretchability of this material, super stretchability, actually around 700% of the stretchability, which implies that we can use this for different applications, including dynamic tissue modeling or wearable electronics, if we're thinking about other applications. So, wow.
Just go into the corner, is it? Okay.
Nice. Okay. So, as I mentioned, our biomaterial inks present shear thinning behavior. But for the simulation that we conducted, we needed to analyze the viscosity law, and we were able to do that and make a fit, and then get the viscosity law for our biomaterial. And take into account that most of the inks present similar viscosity. We just did it for one of the inks, and then we use this expression for the simulations.
So we're going to use this power law relationship to input it into the CFD software to model the fluid. So now moving on to the mixer side of the project. So far, 3 types of mixers have been evaluated. One of them being a serpentine. So it splits the flow into 2 paths, and then there are 2 90-degree turns, and then the flow is recombined. That happens sequentially. And then there's an interfacial surface generator, or ISG as I'll refer to it. And it splits into four different smaller channels, recombines in a hub, and then splits again 90 degrees to the previous ones and repeats. And then there is a chemix mixer, which has helical elements that have opposite rotation direction of So the images that you see are 3D printed from a stereolithography resin printer. And for scale, that's roughly what the size of a quarter would be relative to those. So you can really see how small these channels are. And I just think it's amazing that these resin printers are able to make those small channels reliably, and that they're fusible all the time. It's pretty cool. So what you'll see in the next few slides is that the maximum shear stress in each of these mixers is going to be evaluated using CFD. And the mixing performance is going to be evaluated by mixing fluorescent particles with PEG-TA. So for the CFD analysis, we used Autodesk CFD. And as I said earlier, we used the experimental data to model SILCMA. We used a general turbulence model, K epsilon, and then we computed steady state solutions. So the reason that we want to look at shear stress in these mixers is because cells are affected by shear stress negatively. The more shear stress, the more likely they are to die. So these figures that I'm showing on this slide are from this source. We didn't generate this data. So we can see that what they found is below around 5 kilopascals of shear stress, cells are more or less viable. But once you start getting above 5 kilopascals is when you start seeing significant losses in cell viability. So we use that as one of our design constraints for our mixers. For a given flow rate, we want to keep shear stress below 5 kilopascals. So one thing to note about Autodesk CFD, the software that we used, is it's not able to simulate the mixing of a non-Newtonian fluid with a Newtonian fluid. It's just not something that the software is able to do. So we had to simulate one fluid going through the mixers. So we had to find out which one is determining the maximum shear stress. So what you're looking at is the fluid volume within the ISG mixer. And so you're looking at the very outer surface of that fluid volume, so right at the wall, because that's where the shear stress is highest in this case. So both of these have the same flow rate. One is Silkma only, and one is the cell suspension, which is just modeled as water. And we can see that Silkma has a higher maximum shear stress than water. So we're going to simulate Silkma only flowing through the mixers to try and find the maximum shear stress. So now looking at each mixer individually, again, you're looking at the fluid volume inside the mixer. So where there's nothing is where there's a solid part that the flow is being disturbed by. So we have two flow rates here. One is a slower flow rate. You can imagine if you have a 5 milliliter syringe and you plunge it at this rate, it would take you over 5 seconds to plunge it, which is, it's reasonable. That's slow. And then we chose a fast flow rate that we probably would never work with. I don't think most syringe pumps can even go that fast. But it's to show that even at a non-relevant flow rate, a flow rate that's very high, we're still not quite approaching 5. So that means for this one, we don't really have to worry, hopefully, about hurting the cells too much. Similarly, for the ISG mixer, we see that even at this very fast flow rate, we're not quite at 5 kPa. And for the serpentine mixer, we may exceed 5 kilopascals with 5 fluids. We could, find the in-between those to see the maximum flow rate that we could perfuse at. But if this ends up having good mixing and we end up using it in the future, then we will want to try and stay around this flow rate or level. So now looking at the real life mixing. So we used PEGDA instead of Silkma for 2 reasons. Because it's cheaper and more accessible. It's difficult to fabricate Silkma, as David was describing. So we're using PEGDA, and it also has similar rheological properties and density when it's modified things. So we use PEGDA, and then we have a fluorescent particle suspension. And these are being plunged by this 3D printed syringe plunger. So it has some gears inside of there so that when we push on one of these, when we push on that one, the other one is going to move in a 4:1 ratio so that we don't have to use 2 different syringe pumps and set them to different flow rates. We can use this rig so that we can just do it with our hands. The flow rate won't be consistent, but at least no matter how we push, it's always going to be a 4:1 ratio. So it just makes it easier. So we push on that plunger and both of our fluids go through to this Y connector and they join here and they pass through the mixer into an output syringe. And then we can take that output syringe and cross-link it with UV light. It is UV, but yeah. We cross-link it with light, and then we slice it, and we're able to image those cross-sections. And that's what it looks like. So to quantify the mixing, we select a region of interest. In this case, it's the entire slice. And we measure the standard deviation of the pixel intensity. And then we divide that by the mean pixel intensity. It's giving us a coefficient of variation. So it's showing us, it's giving us a single number to describe how homogeneous the fluorescence is in our region of interest. So you can imagine if this was completely homogeneous, then our standard deviation would be 0. And so lower coefficient of variation is better mixing. So now looking at the individual mixers, we're looking at one pass through the mixer. So if you see in the top right corner, we're plunging our input solution, so the separate solutions, going through the mixer into our output syringe, and we image from there. So passing through the mixer once. Now we'll direct your attention to this complete mixing case here. So this is two syringes just joined together and just forced back and forth very fast, creating turbulence and really mixing. And you would think that the coefficient of variation for a completely mixed sample would be 0, but because there are some artifacts in the image and maybe some bubbles in there, this is about the lowest that we can possibly get with our imaging. And now looking at each individual mixer, notice that the coefficient of variation is above 1 for all of them. So that means the standard deviation is larger than the mean pixel intensity. So it's not very homogeneous. And then when we do 2 passes, so it's gone into our output syringe and then we push it back through the mixer to a new output syringe, we see that our coefficient of variation is dropping a little bit, and the serpentine is even less than 1 now. But you can imagine that if we take off the setup that we have over here and then put a new syringe on, that introduces air into the system and we get bubbles, and it makes it so we can't get mixing. So that's something that we have to try and optimize. I had to really look to find really nice looking images. A lot of them ended up with bubbles. So in conclusion, we developed and characterized a Silkma BioInk and showed its printability and strength. And we evaluated 3 different mixer types. So the next steps for the project are to optimize the mixing procedure, as I was saying, minimize bubbles, and to optimize the imaging process and processing of our samples. And hopefully this will give us more consistent data. And once we identify a mixer that performs well, we can start mixing with cells and look at viability, and finally printing with BioInks. So thanks for listening, and I'm excited to show that to you guys. Yes, that's right. So in Autodesk CFD, we're able to use like the actual power law. So we input the power law coefficient and the cutoff viscosity, and I can't remember what the other number is, but it allows us to input all those things that we found experimentally. Sorry, do you mind elaborating?
So I imagine that the stress will be shear not of the printing. Do you know how, like, what range of?
I'm not entirely sure, but remember that slide that I showed where it showed the viability of cells with higher shear stress? That was a paper that actually looked at different types of nozzles. So you could check and see exactly what the shear stress might be in the nozzle. I think it's actually, it might be higher because some of the nozzles get really, really small. But don't take my word for it. That's a good question, because there's 2 other people on the project, Stephen, and he did most of the research into finding mixers and evaluating them. He's not with us today. He would be able to give you the best answer for that. But I think his inspirations for those was other works with viscous mixing and microfluidic mixing. That's the most detailed answer I can give you. There are some other mixer types that we are looking at that I didn't show just for sake of time and content. And
some of those are modified versions. So like, for example, ribs on the Kenix mixer and other things that we think might improve mixing.
Very related to that mixing question, also related to your other work. What gold standard mixers are out there, commercial products are out there, and how does your system compare to those gold standards? And what would their coefficient of variation be? What are you, sure, your complete mixing is 0.13 coefficient of variation. That's artificial. What's the commercial product, best performing product on the market delivering in terms of and how close are you to that?
I don't
Planted question.
I don't know if there is a gold standard for mixing viscous materials with non-viscous materials, but we did use a commercial mixer. I can't remember what the company was or where it was from, but it's a standard that, bless you, a syringe mixer. So you attach it to the end of a syringe, and it does mix quite well. But I think, does it not have the other connector on the other side? So we're not able to do multiple passes through. So we can do one pass through. And it did, I think if I go back to this, so these numbers are showing around 1.3. I think it was showing like 1.2.
With only one pass.
Yeah, with one pass.
You got 1.1, are you happy?
That's another good question. And we actually
you drop below one.
So we have
two passes. But then we need to optimize then the length of the mixer or other parameters to be able to have those numbers with only one pass. We have actually we tried that, and we were able to get numbers that are similar to 2 passes or 3 passes. But the issue is that these bioinks are usually expensive, and then the dead volume that you're gonna have inside something that is really long is gonna be like huge. So you don't want that. What percent? Pardon me.
What percentage?
What percent of metacritic groups in the Sigma? I mean, for the polymerization, we use Sigma. We don't put metacrylate for the polymerization. The metacrylate groups are grafted to the polymer, right? So what we control is the percent of the main polymer, and the main polymer is Sigma, the protein, and that protein has the metacrylate groups. It's something equivalent to gelatin metacrylate, right? And then what we control is we use 1, 3, and 5%, but of the protein, not the metacrylate.
Which one would you say?
For the inks, the viscosity was similar because we are controlling the viscosity with the rheology modifier, which is clavable. And then you don't control the viscosity with it doesn't matter if you modify the concentration of the protein between 1 and 5, because it's gonna flow anyways. So if you put the rheology modifier, you're gonna have something really similar for the viscosity, which is one of the advantages of our rheology modifier.
So I guess the other parameter size
that could have that could increase the shear stress, right? That's the limitation.
It could increase the shear stress. We could try and predict that with CFD, or we could do a cell experiment and see how much they die. There is a limit to how small we can go because of the 3D printer that we're using. So there is a resolution that we can't get down to. What exactly it is, I think it might be in my lab notebook somewhere, but I can't remember off the top of my head.
So if you're incorporating cells, right? So how do you expect the mixability to change? Because I'm assuming like the cells would be like
You mean the presence of the cells disrupting the flow?
Yeah.
So we have done mixing with fluorescent beads that are roughly the same size as some cells. So we would expect it might be similar. The only thing is those are polystyrene beads, right? So they have much higher stiffness than cells. So maybe there would be some differences. Essentially, we would probably just have to look at the results with the cells after mixing. So comparing it to our models beforehand, we might not be able to make direct comparisons like that. These are giving us an idea of what the best mixer might be, and then we're going to apply that for the cells.
Okay, with that, before I ask for a round of applause for both teams, I just want to mention that we have a reception outside, so don't run away around. We do there'll be one more answer. So let's thank both teams.
So some of you may not know who I am. I'm Jeremy from Department of Medicine, Division of Nephrology. Nice to be over here. Why am I up here right now? I'm up here to promote the 2024 Brockhouse Institute Materials Research Calm biofabrication. I didn't know it was going to come up there. Biofabrication and biomaterials for regenerative medicine symposia. It's April 26th. We've got a pretty stellar lineup secured already. Lisa Radisik, Stephanie Willard, I'm Feinberg from Carnegie Mellon. Sarah Gilpin, who works for Estelle Pharma in regenerative medicine and worked at Life Institute with BIMR. She'll be coming up from the States. Axel Gunther from U of T as well. So it's a pretty good lineup. We were oversubscribed last year. We couldn't have anybody else attend that was at the faculty club here. So April 26th, mark calendar advertising. We'll be going out with Florian, helping with the advertising. I think registration is actually open. So mindful of that. And we hope you can participate. There'll be a poster session as well. So, yeah. Thank you.